we sell as a catalog. So the focus for this talk is on product matching and a very specific problem we encountered there and how we made it faster. Yeah? This is the outline of the presentation. I'm going to spend a little bit of time giving you context on what product matching is and how we approached it as a search problem and quickly figured out why search problem isn't necessarily cutting it and reconstructed it as a similarity search problem and the infrastructure and scaling challenges we hit along the way and the key takeaways. Yeah, with me so far? Okay, what is product matching? Here we have two products, right? Can everyone see the picture all right? So we have two products. An Apple iPhone 7 128 GB in jet black, and we have an iPhone 7 32 GB in black. Are these two the same product? Not really, right? Because one, they have different storage and they're also of different color. So this magic box which makes this decision is the product matching model. Why is this important? Imagine if you want to do a price comparison between the same Apple iPhone that is sold on Amazon and Flipkart. The only way you would be able to compare the prices is if you are able to match the products. And any product level statistics, if you want to understand how many iPhone 7s are sold on Amazon versus how many are sold on Flipkart, you definitely need to be able to match it. And then another interesting use case is feature enrichment, where one site might have all the required information about the product, the other might not. So when you're able to match them, even with limited information, now you can take the rich features from one site and merge it with another one. So that way you have a richer product. And yeah, it makes sense. It also makes sense to remove duplicates from your catalog just to ensure that, generally the catalog is of a good quality. Okay. Now, I noticed that some of you thought the Apple 7 128 GB and the 32 GB, both in different colors, were in fact the same product. That is a fundamental distinction. So let's go a little bit and figure out define the problem clearly and nail down what is a match and what is not a match. So here we have Apple's iPhone 7 unlocked 128 GB in jet black. This is also 7 128 GB in jet black. So at the feature level, all the attributes are the same. So this is a match. However, in this case, this is 128 GB and this one is 32 GB and this is black and this is gold. So now we know when do we say two products are a match and two products are not a match. So great. We have this magic box, right? And however, when we are trying to do deduplicate, we have this input product, and this could be any product in the catalog. So this poses a very interesting problem. So if we were to solve this, one naive approach is to compare every product against every other product in the catalog. But then this doesn't really scale very well. If you have hundreds of millions of product in your catalog, the number of every time you want to deduplicate, the number goes up way high. So we could do a little bit better and compare it only against products which are in the same parent category. Let's say it's electronics, then in the stages of the pipeline, since we already do categorization, we can already understand that the product is of electronics, and we can only restrict it to that search space. But then there could be so many products in electronics. This doesn't necessarily, this reduces the search space, but not so good, right? We could take it all the way to the leaf level. However, this could also, then you'll still have to match it against all the mobile phones. Or we could do even better. Only compare it against a set of similar products, right? Now, how do we find products which are similar? Yeah, given a product A, how do we come up with the candidate list of M products which are very similar? Yeah, the moment I saw this, yeah, it's so simple, right? It's a search problem. You have input data, and the input data has a lot of attributes. So now I only need a way to search it and get all the products which are similar. This sounds so easy. Take all the products, index it into Elasticsearch, and then whenever you have a new product, query it against Elasticsearch. Whatever result that you get, you send it to your product matching system. So this is what I was expecting. So I search for Apple iPhone 7. It neatly gives me all the products which have the same attributes and are very, very similar to each other. But this is when reality hit me. So I searched for Apple iPhone 7. It gave me one product. Okay, fine. iPhone 7 32 GB in space gray. But then where the hell did this come from? So now I have a harsher case and screen replacement, right? So if my search is showing up all these products which are definitely not a match, then I'm doing so many useless comparisons. So why does this happen though? I mean, so it has all the products that all the important keywords in the search query. So the results also do have some amount of the important search query. It has iPhone, it has iPhone, it has iPhone. So looking deep into this is to do with how Elasticsearch internally represents this text as a vector. So it takes this text, tokenizes it, and creates a gigantic TF-IDF vector. So the problem with TF-IDF is that it creates a very, very sparse representation. And when the representation is so sparse, all the semantic meaning is lost. So from the result, if we noticed, the major reason why this is happening is that the result hasn't really obeyed the semantic meaning of the search query or whatever we are trying to search for. How can we fix this? Okay, one easy way could be to, since we already have information about what category something belongs to, and also we know all the attributes, can't we just use all the structured attributes in the input product and use that to further reduce our search space and query it? The problem is that we are just talking about mobile phones. When you scale it to all the products that are all the e-commerce products, you have each category itself could have hundreds of different structured attributes. And even though these are structured doesn't necessarily mean it is in a particular form. This is still textual in nature. You are still going to have to run your free text queries on what is supposedly structured. And this way, what we are also doing is we are putting very, very strict quality standard on the input query itself. So this is a non-starter for a use case like feature enrichment, where your input may not be so rich, but you still want to enrich it. Naturally, so we did try this. we did try using structured attributes in our queries, but one thing that happened was the, the queries were getting a lot slower. Our latency was our latency for this system was sub-second before, and then when we made this change, it jumped all the way up to 1.5 seconds to 2 seconds. There should be a smarter way to do this. So yeah, it's a similarity search problem. What if instead of me hand engineering all the features and also hand engineering the query, I have a model which can understand all of this attributes, and the model can tell me what the similar products are. How are we going to do this? So this is my input product, Apple iPhone 7, 128 GB jet black, GSM and unlocked, and this is the product's image. So this is the magical model that I want, which is going to take all of this information and embed it in a vector space. Right? If I have this embedded in a vector space, then what I can do is this vector space now becomes my search space, and I can use this input query and the vector representation of this input query and query for all its neighbors. So that is the key idea here. Before we dive further in, let's try to peek into a model and see what it does. So before anything can go into the model, we want to make sure we are able to represent it into a vector in as crude a manner as possible. So as this product in its vector form makes its way through each layer of the deep net, what is essentially happening is the vector space keeps getting transformed. So at one layer, at this layer, this is what the vector space looks like, and this layer, this is what it looks like, and finally, this is what we want. So this is essentially what happens in any neural network. So you have your input in some vector form, and when it goes all the way through different layers, the vector space just keeps getting transformed and transformed. So one of the ideas that we wanted to try was we already have a way to categorize this product. And this categorization is, our categorizer is a neural network. So at this stage, the final softmax tells us which product category this product belongs to. So now what we did was we took the layer of output of this layer and used that as our vector space representation. So one interesting thing that happened is now we have 3 different iPhones, and all of them with these two are the same, 32 GB rose gold, 32 GB rose gold unlocked. And then we have, this is the most interesting bit here. We have 128 GB black and then AT&T. If you notice this, 2 of these products are the same. It makes sense for them to be closer to each other. There is no reason why this should be closer to these 2 as well. The reason this is happening is because how we generally train our categorizers. When you're training your categorizer, the objective is completely different. The objective is to group all the products belonging to the same category closer together in the vector space. But this is not what we wanted when we wanted to do product matching. So how can we fix this? Okay, Siamese twins to the rescue. So we took the same model and shared the weights. So at the end of this, whatever vector output that we get, we added a final dense layer on top, and then we back propagated with contrastive loss. So after the set twinning or twine tuning, this is what the vector space looks like. So earlier, the 128 GB iPhone 7, which was somewhere here, has now moved all the way here. This is good. Let's see how this works when we actually put it to test. Okay, so that worked. We have all the products. This looks good. We have, this is not the same. This is a variant, but that's okay. My model can handle that. So we have a way to represent the vector, and we also have a way to identify if two products are similar. In order to take this and put it into production, the only thing that was missing was a search database. So there are several options. So there is this website called the ANN Benchmarks, which has benchmarked all the popular nearest neighbor search libraries out there, and that was our starting point. Of all the options that we saw, most of the available options were libraries, and they were built to work on really small data sets or data set that could fit into memory. And it takes a considerable amount of time to build or rebuild these indices. Out of all the options that we tried, phase is what we settled on. Phase came out of Facebook research. So there is this really famous paper called Billion Scale Similarity Search, where they are able to take like a billion images, pass it through ImageNet, and are able to get like 8.5x the speed up over existing methods. And one really cool thing was that it has inbuilt support for product quantization and vector compression. So even though we are creating really dense vectors here, so these dense vectors could end up being really, really, really large. So now you have hundreds of millions of vectors, and all of these libraries they are designed to fit into memory. If you don't have quantization or vector compression, we are dealing with a lot of memory here. So we tried it out. We were able to index 60 million vectors in a day on a single M4 extra large. And the entire index of 60 million vectors was less than 4 GB, and we could easily fit it into memory. And get this, this was the most impressive bit of all. It had amazing read latency. We were hitting like 390 milliseconds at k equal to 100 if we were not doing batching. If I were to batch the queries, our read latency amortized over the batch was 19 milliseconds. So to put it in perspective, Elasticsearch was taking anywhere from 1.5 seconds to 2 seconds per query. But it's only a library, not a database. And we want to use this in production. So like we saw, the numbers are too good to be true, and it works. What can we do to make it work and take it to production? So it was time for us to ask if we really, really, really needed a database in the most traditional sense. So our workload is predominantly read heavy, and we wanted it to be highly available. We were okay with the data being slightly out of sync, but we wanted it to be highly available. And we were okay if it was doing batch writes. So going over all the requirements again, it turns out we didn't really need a database in its traditional sense. So what we pretty much ended up doing was we took phase and slapped a network proxy on top of it, and it worked for us. But what about the writes? The only problem with this approach is that if I want to scale writes, the only way I can do it is to vertically scale the scale the machine. So one workaround is to just keep one master index, and all the writes go to that master index, and this master index is not going to be available via network. So whenever we want to write it, it's going to be in batch mode, and once the writes are made, we'll replicate the master index across all the available read replicas, and make the reads make them available, make the new writes available for reads. So this is what our key benchmark, just to tabulate our benchmarks, this is what it looks like. Our recall at 100 with Elasticsearch was 91. It jumped to 95 when we were using Phase. This is mostly thanks to the better representation. And the most impressive bit is how our read latency went from uh, anywhere from 1.5 to 2 seconds to 390 milliseconds. And if you were batching it, it was 19 milliseconds. And our cost for every 100,000 deduplication went down from $300 to $30. Throughout this whole exercise, these are key lessons. Tuning Elasticsearch can only get you there is only so much you can do with Elasticsearch. You need to know when it fits your problem and when it doesn't. And dealing with fuzzy queries with a lot of variable information isn't easy. In our use case, that there could be a lot of fuzzy queries. These inputs could come from any of these retailers, and they need not necessarily strictly adhere to a particular schema or a particular query standard. And search is only as good as its representation. It's not really Elasticsearch. It wasn't really Elasticsearch's fault that when we were searching it, we weren't getting the most similar results. And use case specific solutions like what we ended up doing here could be a lot more cost effective. In this case, our latency went down 5x, and also our cost went down by 10x. So yeah, if you have questions.
Hi, thanks for the talk. So I just wanted to understand a little bit about the Siamese network that you use here. How did you generate the training data for the Siamese network? Also, I have another question. So I think in doing the similarity, the assumption is that you have structured data. Have you tried this with unstructured data as well? And how? What were the insights there?
Okay, that's a great question. So to answer your second question, no, we haven't really tried it with unstructured data. One thing that worked really well for us is that when it goes before it hits this stage of the pipeline, we have our categorization and NER, which extracts a lot of this structured information, which can in turn go into the model. So that really helped for us. With unstructured data, what kind of unstructured data are you talking about? Are you talking about something like we haven't tried it with just the title. So if it is something like images, you could try what FaceNet does. To answer your first question, there are multiple things that you can do to generate your input training data set. You can do something like triplet mining. Maybe I can share the paper with you later. So yeah.
Next question. We'll stick to one question per person so that we give chance to everyone.
Yeah, so when you did compression in your dense vector space, so you already have dense vectors and then you further compress them to whatever degree. You showed the improvements in the speed, but do you know how much of a cost you paid in terms of your model similarity metrics? Because now that you're compressing, your similarity matches are going to take a hit. Do you have a comparison there?
Yeah, it wasn't re- it wasn't really significant for us to completely abandon the compression. So the trade-off wasn't that high. It was probably like a 0.5% drop. So we were given the uh, given the infrastructure reduction in infrastructure cost, it made sense for us to go with the compression than to than that 5%, the 0.5% boost that we are getting.
Hi. So my question is regarding the Siamese architecture. So onto the Siamese heads, what actually goes in? Is it the when you said product is the information that goes in? So is it actually the image of the product, or you are combining the image and the text in any way? And if so, how are you combining it?
No, so here maybe that image was misleading. When we send it to the Siamese network, we don't actually send the image. It's only the product information which is structured. So when we process the input, we have different attributes, and these different attributes are encoded in a particular format and then fed in. We are not really combining both the text and the image, at least in this version of the model. But yeah, so if we wanted to do something like that, there are a lot of multimodal techniques that you could use. So one simple way to do it would be to take the output vectors of both of you. Have two different models, one that encodes your text and one that encodes your images, and you merge these two vectors by simple concatenation and train the entire model together.
Have you done this experiment?
Uh, no, it didn't really work out that great for us, but yeah, we are working on this.
Alright. So what worked best was just sending the encoded textual
Yeah.
features into it.
So you extracted the second last layer of the network to generate your vectors, right? Do you assume that you know the categories ahead of time? Or, I mean, at least the number of categories?
Yeah, so we have a fixed, our category tree is hierarchical, and we know which these categories are enumerated, and we know what those categories are. So there are only a fixed number of labels this classifier could classify a product into. More questions?
Yeah, so there's a lot of attention on Siamese networks. So, I mean, this might be a combination of all the questions, but just to clarify, the first network had categories as the target variable, right? And that obviously nothing is there to kind of tell it, kind of have a life on 32 GB is closer, should be closer to 128 GB. Then you use Siamese network. What exactly is the dependent in the Siamese network?
Sorry, I didn't get you.
So what
I
exactly
didn't
is
get the last part of
what
your
exactly
question.
is the target variable in the Siamese networks?
Okay, so the target variable is a Boolean saying whether they are a match or not.
Okay, so the first network had category. The second is, so I mean, what would be the structure of data like when going to the Siamese network? So you have that last layer input, and then you have a dense layer. So what exactly is the?
Oh no. So when we are actually training this model, we don't freeze the last layer.
Okay.
So when it is retrained, it's retrained from scratch.
And the output is what SKU is it similar to, or?
Yeah.
Okay.
Any other questions?
Hi. So when you did the comparison with Elasticsearch, did you tried optimizing it as well? Like there also we have weighted queries. We can add weight to the category, so it will give more weight to the similar category features.
Yeah, that's a very good question. We actually did try that. So going back to my slide, I think it's this part. Yeah, so we did try it. So that's what I was talking about when I said structured attributes. So we did try that, but then here the problem is that you have, for example, if you look at our category tree, there are like 20,000 different categories all the way up to the leaf node. So now if you want to target this makes sense when you doing hand tuning this for Elasticsearch to get it to work makes sense when you're only working on a particular set of categories. Say you're only trying to solve this for mobile phones or you're only trying to solve this for laptops. But then when you want to scale this across multiple categories, then it's like a lot of hand tuning that you would have to do. What happens when you have a new category? These category trees are updated from time to time. And also sometimes customers come in with their own category taxonomy, and we also want to be able to accommodate that.
I was just curious if you have compared FAS with LSH.
We did a mini experiment with LSH, but then there is this library called Data Sketch. We did they have all the different types of LSH algorithms that you want to try. We did a mini experiment with it, but it was not really warranting enough to take it and start using it at a large scale.
So was it the scale that was the issue, or was it the accuracy?
No, one, the way it creates the hashes. So with LSH, the way it creates the hashes and weight queries were like tightly coupled. So here this allowed us to use our own vector and do nearest neighbor search. It gave us the flexibility of bringing in our own vector representation instead of having to rely on something that comes in with LSH.
Thanks.
So if we were to redo this again, we'll probably use something like SP tag. Microsoft recently released an open source project which does something very similar. It's a database. It's a library come a network service which allows you to do vector search. So in this case, we didn't really want to go about building a database. We wanted something that would work, that would put this behind a network and allow us to move fast. So, but then here we were compromising a lot in terms of how we could do writes and how quickly we could get new data into the indices. That project from Microsoft solves it in a much more mature manner. If we were to redo it again, probably in the next version, we'll definitely use something like SP tag.
Does anyone have a question? 3 more minutes left.
So with this you achieved essentially similarity search, right? So did you take this further to identify exact duplicates within that neighborhood?
Oh yeah, so that was not really the scope of this talk.
Okay.
The scope of this talk is specific to how we are doing similarity search. But yes, so this is not the product matching model.
Yeah.
So with this, what we are essentially doing here is to generate candidates to be fed in as input to the product matching model.
Right. Sure.
So no more questions. And does anyone have a second question or something? Thank you, Abhishek, for wonderful session on similarity search for product matching. So the next session here is improving product discovery via hierarchical recommendation. We have a speaker, Neha Kumari from Flipkart, and she's a senior software engineer at Flipkart, and she's an alumni of IIT BHU. So over to you, Neha.
Hello. 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 Am I audible? Yeah. So, good morning, everyone. I hope you guys are enjoying Fifth Elephant Conference this year. So, I'm Neha, and I work as a senior software engineer and recommendation team in Flipkart. So, today I'll be talking about improving product discovery via hierarchical recommendation. Uh, So before we get into the talk, let me ask a question to you guys. Imagine a scenario where a user is trying to purchase a laptop decal, which is a screen guard which we put on the backside of a laptop, and the user has landed to this product. So as you can see, it is a laptop decal which has a like Ronaldo cover, Ronaldo photo on it. So what should we recommend to the user in this case in order to serve his interest or his intent? For this, I'll give two options. First is either we can show a laptop decal which has a graphical picture on it. Second, we can show a purse to the user. A quick show of hands, what do you guys think for the first one? If anyone thinks we should recommend first, or and second one. So yeah, as we can see, the audience is like fairly divided here. So it is very intuitive for us to think that we should recommend another laptop decal because it is in the same category. And since a user is already on a decal page, he might want to browse more from the decals. If we talk about option two, since from the parent product, which is the pivot here, we can see that user has a fairly high interest in Ronaldo themed items. So if we recommend the user other Ronaldo themes product, it will be a high chance of him converting it, as in it will be high chance for him to adding it to the cart or maybe buying it. So with this context in mind, today I'm going to explain, or today I'm going to talk about how we can build such system, build such recommendation engine which can help us derive such counterintuitive data patterns or such counterintuitive patterns to recommend, which will be serving users interest at a very high level, as well as will be very much converting for our business use case. Just to give the overview, I'll briefly touch upon about what a traditional recommendation system look like. Then I'll talk about what are the problems in the traditional recommendation system. And then I'll go about our journey, Flipkart's journey of solving it. And finally, I'll conclude my talk with the takeaways. So yeah, introduction. So this is a standard or traditional recommender system where when you want to generate relevance between two products, what you do is you take multiple signals which can be a user generated signals, like user doing a browse activity, user browsing through several products, user adding the product to their wish list, user adding the product to their cart, or maybe purchasing that order, co-browsing the particular products in the same session, etc. Along with that, we also take product attribute into account, which actually tells about the product feature. For example, in case of mobile, what brand the mobile is. In case of, say for example, a lifestyle product like kurti, what pattern the kurti is, what is the size of the kurti, what is the color of the kurti, etc. As it is fairly evident, we use a mixture of content-based and collaborative filtering, where collaborative filtering talks about the historical behavior. As in, if two product has been purchased together, it is a fairly high chance that tomorrow second user will also purchase those two products together. So yeah, we mix all these signals and then we generate the relevant candidate set for a given parent product. Once we generate the relevant candidate set, we then re-rank those candidate set in order for us to serve to the user. As in what order should we serve the product for the user to convert more, so that it can serve the user's interest in the best fashion. So in Flipkart, our optimization function is like conversion. So yeah, our logistic regression model optimizes or re-ranks the candidate set as per the conversion of that particular candidate set predicted. So when we saw the traditional recommender system, it looked all okay to us, but there might be some problems which might not be surfacing at maybe at a first glance, but it might become a bottleneck for your business when you're talking in terms of like long tail categories like lifestyle, etc., where the flux is a lot and the products keep on changing at a very high frequency. Like you might have thousands of thousands of products adding to your catalog, getting added to your catalog every day or maybe on a weekly basis. So what was the motivation for us to like come up with the hierarchical recommendation, or what was the motivation for us to do in follow any such approach or algorithm? So yeah, the first motivation was cold start. So I still remember the scenario where Kama Ayurveda, which most of you might already know, it is a high ASP brand, like high average selling price brand. So the Kama Ayurveda got launched in Flipkart, and our category managers came running to us that we are showing a low ASP brand like Parachute or Nivea along with Kama Ayurveda. That was a failure scenario for us. What we could have done is we could have shown another high ASP product like Forest Essential, which actually has a very costly products, along with Kama Ayurveda, so that it could serve the user need. So why it was such? Because there were, since it was a newly launched brand, there were no much user behavior or user browse pattern on top of it. So we didn't get any browse data in order to generate the recommendation for the parent product. And that was the reason that we were recommending low ASP product along with the high ASP product. And this can happen in any other scenario as well, where a new category or a new brand is getting launched in Flipkart or any other e-commerce service. Second was post-purchase engagement. So suppose a user comes to Flipkart, he purchases something, and then he checks out, and then finally our delivery service eCart delivers it to their doorstep. But what after that? Are we done with the user? No, we still want user to be involved with us, to browse our content, to purchase more. In those scenario, what we can do is, suppose a user has purchased something like a workout gym clothes. Then since we know that, sorry. Yeah, so since we know that, oh, sorry. So since we know that user has a very high affinity toward gym clothes, we might purchase other collection like some books on healthy eating, healthy lifestyle, or maybe some other gym equipments like maybe gym gloves or zipper bottles, etc. So that was another motivation for us. The third was search result augmentation. So yeah, in this example, user has fired a query like Banarsi sari. So what we can do is we can recommend some more collection which is highly related to Banarsi sari. For example, the fabric which is matching the most to Banarsi can be silk. So we might recommend user some collection from the silk saris or maybe Kanjivaram sari in order to solve the user need in a much broader sense, and user might get interacted, or maybe we will be able to surface our catalog content more to the user. So it will ultimately improve the discovery of the catalog of ours. So after stating the problem, let us see what can be the solutions for it and what was our journey for that. So for this, I'll first explain how we have structured our category or how is Flipkart taxonomy built. And then I'll explain the basic algorithm for computing the relevance. And then we'll talk about the multiple approaches and design consideration and then the comparison of approaches. So let us first start with the Flipkart taxonomy. So in Flipkart, we have almost around 5,000 plus category and we maintain them in a tree fashion. Here you see the parent node is consisted of all the categories which lies inside Flipkart. It is like broadened enough to have like fashion, electronics and everything. And then it is categorized like category, subcategory, subcategory, etc. So if you see footwear here, we have a whole range of like shoes, sandals, slippers. And shoes will also encompass from casual shoes to running shoes, sports shoes, party shoes, etc. So this is how we have structured our all the categories in Flipkart in a tree fashion. And in future slides, we'll see how we'll generate recommendation or how we can generate recommendation at each of those nodes or how we can leverage this structure in order to generate recommendation. So yeah, now we'll talk about how we can compute relevance via cosine similarity. So as we all know, cosine similarity tells me what is the theta or what is the distance between two non-negative vectors. So here, just to state the formula, it will tell me the total number of times two products have been browsed together divided by the individual number of times those products have been browsed. So in this example, I'll just pivot on the algorithms book to be the parent product. I'll try to derive the similarity between the other two books which are here, computer networks and 5.1. So as we can see, the 5.1 has been individually browsed a lot, but since it has not been browsed so much with the algorithm book, the computer networks, it actually wins over it. And that is quite fairly obvious as well, because a user will try to buy those two books together as compared to the other two. So yeah, this is the basic and the fundamental algorithm which we use in our data pipelines in order to generate the relevance or the similarity between two products. And then we do a comparison whether A wins over B. Yeah. So going into approaches, the first approach which we did was content matching. So content matching is actually a product level approach where in the taxonomy, if you saw, we had the lowest node. The lowest or the leaf level node will have all the products. So here we actually match two products, which is an exact match. These are actually the production example. If you go on Flipkart website and if you search for MITV, so you will get the right hand side product on the recommendation. Similarly, in the sari example, if you search for any pink floral sari, you will get the other sari as a recommendation of the first one. So how do we do this? We do exact matching. If you see here, both of them are matching in terms of their brand, display size and screen type, and the smart TV being yes or no. Similarly, on the other side, for sari example, both of them have their material as chiffon. Their pattern is floral and their color is pink and type is daily wear. So this is how we are doing it. We have a full range of catalog which has indexed all the products, and then we do a matching on top of those products within a category. But now let us talk about second approach, which is entity matching. So entity matching, this is done at a higher level or a category or subcategory level. If you remember the taxonomy which I showed you, so there are categories like electronics, lifestyle, etc. So now what we can do is, if a user has fired a search query like tunics, so we can pivot around this tunics, which will become our entity now. So now we'll try to derive the relevance between two entities. Here, tunics goes well with, as in tunics is relevant with tops, kurtis, shirt. So this is the collection of product which we can show to the user that, okay, since you have searched for tunics, you will also be interested in tops, kurtis, shirt, etc. And it will have the like corresponding relevance score of S1, S2, S3. Similarly, if a user is searching for bread toaster, since we know that user is already very much interested in like toasting and all those breakfast things, so we might try to recommend the user another things like electric heater or coffee maker or hand blender, things like that. So yeah, this is done at an entity level where we try to find the relevance between two entities. And the entity we can define as a category or the subcategory node which I showed earlier. So the third approach which we used was cluster matching. So cluster matching can be a combination of an entity plus multiple facet, where a facet is actually an attribute. Let us first understand this first. So here example is red crop top. Here what we can see is that top is an entity because it was there in the category node and it represents one full range of products. Red is one facet which is a like filter which has the key as color and the value as red. Second, crop is another filter which has a key app type and value as crop. Same of in case of jeans, we have like facet as black, which is color, high waist as type, and jeans is another entity. So this is how we can define a cluster where, and then we can try to find the relevance between two clusters again via the same relevance generation or the cosine similarity method. So this approach actually tells about how well does one cluster matches with another. For example, how well does a red crop top goes with a high waist jeans, or how well does a Levi's white t-shirt goes with, say for example, like some Vera Moda jeans, blue jeans or something like that, right? So we have tried to solve it at this level so that it can, if we again go back to the like Ronaldo example. So now my system will be completely fairly able to generate recommendation at this level, and it will solve the user need in a very highly specific manner. So yeah. So let us go deep into how do we come up with such cluster, how do we generate such clusters. So first of all, we have the taxonomy which I showed. So we have the taxonomy and we also have the user's raw data, which is like user explicit or implicit interest. So when you go to any e-commerce site, either you can search on the search bar, or you can also apply filters on the left hand side, which is present on the left hand side, which will try to like poke you about like what brand do you want, or maybe what color do you want. Do you want front loading machine, washing machine, or maybe top loading or something like that. So we take users interest and then we take taxonomy as well, and then we try to generate popular facet or popular filter per node or per category, which will tell me in case of mobile, like the OS can be one category where users just go to the type mobile and then first of all search I want an Android mobile. Second, it can be like I want like Wi-Fi mobile, Wi-Fi enabled, FM enabled and things like that. Similarly, in TV, a user can go and say that I want an Android TV and I want a like Chromecast TV and etc. things like that. So those are the filters which we can apply, and this first block deals with that at a particular node level it will try to find all the popular filters. Then once we have that, so yeah, the output of this will be, if we talk about the sari as a category, it will give me color, pattern and fabric will be highly popular filter in this, because most of the user have been trying to express this via their query or maybe via expliciting, going and selecting the filters. After that, we generate the popular facet value per node into facet key. For example, I have seen that sari goes, I mean, color is very popular in sari, but what color exactly? So that can be one question. Again, pattern goes well with sari, but what type of pattern? Same with the fabric. So if we talk about this block, the output of this block will be like, in case of sari, the color will be red, pink and green, because most of the women, they search like red saris, pink saris or green saris. Whereas if we talk about shoes, it will be blue, gray and white, because most of us try to, I mean, most of us, it's in fashion that we wear blue, gray and white. So it can depend on a category into like facet key level. As you can see here, it is different for shoes and different for sari. Now, after we have this category into facet key pivoted, generated popular facet values, we then try to generate the cluster, which is nothing but just a hashing function, which will give me some like hashed value out of, for a particular node, all the hashed value which I can get from this block, and then I'll just put my data into HDFS for as an like storage, and I'll try to use it in my relevance algorithm. So yeah, what were the design consideration which we did as a part of this? So first was pre-computation, like runtime creation versus the pre-process and pre-computed index of cluster. Like, do you want to generate your cluster at the runtime? Yes or no? Definitely no, because the popular facet or maybe the popularity of a particular facet doesn't change so much on a daily basis. Like there might have been 100 set of users who have been doing this since a very long time, and we might try to generate those clusters offline, as I explained in the algorithm earlier, and put it in our storage so that we can use it later in our algorithm. Second can be the cluster definition. Like as I said, a cluster is defined as a node plus facet key into facet value, And how many facet key do we want to consider? That is the question here. What can be my K here? So if I see in case of sofa, as soon as I search for sofa, my choice can be a sofa which can be a 3-seater, a sofa which can be 3-seater and wooden, a sofa which can be 3-seater and wooden and contemporary style as well. So what it is that user pivot on the most. This can be flexible depending on your category as well, because in case of mobile, you might just want iPhone 7. In case of like sari, you just want red floral sari. Or maybe in case of dress, you might black, mini party dress, something like that. Yeah. So it will depend on a category level as well. So this K can vary per category, and you can have it as a configuration in your algorithm. So for us, we actually experimented with like K being 2 and 4 and all. So 3 is the number which became optimal for us, and we went ahead with that to solve this problem. Now, the other thing which comes is like top facet. So you want to increase your coverage, but you should not degrade your your quality as well. So you should not end up considering all the facet in the world or all the facet which can be applied to a particular product. So you should only consider what is the top or maybe the popular filters which have been applied by or which are being applied by the users. And it can again vary from category to category. For example, in case of mobile, brand is more important than screen size. In case of a woman top, color is more important than pattern. In case of sofa, seating capacity is more important than color. Like none of us mostly worry about the color as much as we worry about the seating capacity when we go to purchase a sofa. So yeah, as I mentioned, this also varies from one category to another category. So how do we, after we did this algorithm and after we generated the data for this, how can we measure the improvements of it? First thing, we definitely run the A/B test to find what is better in the control and the test. And then we went live with that. Another thing which can be like serving efficiency. If how much I'm able to serve to the user, which is this, if we want to define it mathematically, it will be like the number of response I am able to get to the user per request coming. So the number of widgets I'm going to fill on my home page or product page divided by the total number of requests which is coming to me for that. So in this case, this is again a production example where a user has purchased a juicer, a mixer. Since we know that user is trying to fill his kitchen with appliances, we have actually recommended him a collection of other kitchen appliances. He might be interested in buying the electric jug or maybe cookware or casseroles or gas stove, etc. Another example for this can be this gym or sports example which I gave earlier as well. So since the user has shown interest in some of the athletic activities or some of the athletic products, we might want to show him a cricket bag or maybe martial art equipments, fitness supports, fitness gloves, etc. So yeah, this was one of the metrics for us by which we measured the improvements or the goodness of this algorithm. The second one can be coverage, like how much of your catalog data are you able to cover by the recommendation which you generate? Is there any such chunk of the data which is not yet being covered or which is not yet being recommended and you are losing your customer because of that? So here, as we can see, the like the fabrics which are very closely related to Georgette are like art silk, Georgette and chiffon, etc. So that is how we measure that, how this in crux tells me about how much of my catalog I'm able to generate the recommendation for. And the third can be conversion. As we all know, conversion is what we care about. So if a user is clicking on particular website, a particular product in your website, then is he finally going to buy it or not? And that is what we measured via our A/B testing as well. So if I just have to recap the approaches which I talked about, the first one was content matching, where we did the matching of the products at the lowest level or the leaf level of the taxonomy. Second was entity matching, where we did the matching at a higher level or a category or a subcategory level. The third can be cluster matching, where we did a combination of a particular node or a category with multiple facets applied over it. So let's do a comparison between these approaches, whatever we have done till now. So if I just do a comparison, so the major thing to compare for me will be the coverage versus the sparsity. When I generate recommendation on a like lower level of the product level, the sparsity will be definitely very high, because I'm talking about each of the products there and trying to match them. Whereas if I try to like generate recommendation at a cluster level, the sparsity will be very low, but the coverage will be high. Because a user might not go and browse a particular product, but he might have bought that particular cluster, as in he might have bought that browsed that particular category sometime in his life, and we can then reach to the products from that category. Once we expand that category, it will automatically lead to a very huge set of products for which I'll have recommendation at the end of the day. And entity matching actually lies in between these three. So yeah, that was a comparison. Now, if we just have to take a look at the summary of whatever we have covered till now. So first we talk about the introduction, and then the generic recommendation system and what were the issues, and then what were the solutions and the evolution of methods, whatever we have achieved till date in multiple iterations of our experiments. The third one was deep dive into solution and the metrics, as in how can we measure the improvements. So to conclude my talk and to give the key takeaways from it, we actually talk about the problems which might not be very obvious, but it might actually be a bottleneck for long tail categories like lifestyle. And then we also talk about how moving away from product to product and generating recommendation cluster to cluster level, it actually helped us solving a lot of problems like cold start, post-purchase engagement, search result augmentation, etc. And then we did a comparison between how to which algorithm to choose and when we are talking about the coverage versus sparsity metrics. So yeah, with this I would like to conclude my talk, and yeah, any questions, anything?
Yeah, first question. Mike, question.
So just to circle back on the example,
Where is it? Oh, sorry.
just to circle back on the example that you gave at the very beginning, could you give a concrete sense of how the techniques that you developed actually helped you recommend the Ronaldo themed purse rather than
Yeah,
because electronics and accessories are also completely different categories.
yes,
So from your figure, it wasn't clear
Yes.
how you were making a cosine similarity measure between cross
yes.
categories. for
So
example.
again, so when we talk about cross categories, it might not always be possible that you will serve it in always in your similar recommendation. You might serve it as a cross recommendation as well, right? So from there, when we generate cosine similarity between two products, then we keep a threshold on top of it, that if it is reaching a threshold more than this, then I might consider it for my cross category. For example, in a past purchase of, so for that example, the base for us was the user order data. So if a user has ever ordered a laptop decal with the purse, then we might know what are the two parent level categories for those two, and then we will match the faces of those two, that what is the theme inside them, right? Now my theme is matching. So once I match the theme, I have a very high similarity score for these two guys, like for the laptop decal Ronaldo theme and the purse Ronaldo theme. That will beat the threshold of the laptop decal, and then laptop decal being the graphic laptop decal, and then the purse. So yeah, that is how we came up with that.
So next question. Actually, we'll have to give one question per person.
We can
One
catch up offline, that should be okay.
The next question, please. Here, the first two rows of questions.
Hey, yeah. So you talked initially about taxonomies, right? So I have one question. How, in the cold start problem, how do you actually generate the taxonomy? And the other is, if a new product comes, how do you put that in a taxonomy order?
Okay. So we have a separate team with us for that, which is a catalog team. So they have some tags with some seller, I suppose, and then they have provided them some interface by which they can add their products after being verified by Flipkart or by our services. That if they can add their product to our Flipkart catalog or not. And then that team does the tagging and putting. So on the basis of the attributes, we group a set of products together, and then we put it. Say for example, you want to put guitar, electric guitar, and maybe acoustic guitar. Both of them will be again put in the same particular node, but they are different. But they're matching on some of the attributes. So that is how we group them together. We're matching their attributes or grouping them by their attributes. That is how we come with. Yeah.
Last question for the day.
Yeah, can you also talk a little bit about how you're identifying the facet for the category?
Okay, yeah, so this is again, it is done by, we have a search team. So they are coming up with the top facet or maybe all the facet which can be broken down from a particular category or a particular subcategory. So that will tell me, if I'm talking about sari, what can be facet which I can apply, and then I can serve those results. Like if you search something on the search bar, you will get a full results of the whatever products is being shown there. Then you can apply filter and it goes down and down and down, right? As in many number of filters you apply there. So yeah. For generating the popular facet or just deriving the facet? The relevant facet, that is what we are using via the, like as I told, there are queries which are done by the user, and also there are explicitly user are going and searching or clicking the facets there. So that is what I'm doing. The number of queries came and the number of facet which is present in that particular query. So important queries divided by total number of queries. That is just a normalization thing which we get. That is a very naive approach. We are in the process of evolution for that.
One more question.
So I have 3 queries. First
No,
one
one
would be
query, lo.
Big one.
so first one would be how can you comment on shared devices? Let's say my account might be shared by my friends. Okay.
Okay.
So you need to show 3 different recommendations for 3 different devices,
Yes.
and location of a account might also matter.
Correct.
A person shopping from
Correct.
Bangalore might
Correct.
probably looking for a silk saree,
Yes,
but
correct.
same silk saree will not be looking
Correct.
for. But during your presentation, you never explained about any user level features.
Yes, because this presentation didn't had that scope. But yeah, that is one thing which we are in the process of building, where we are taking user demographic in context. As you said, right, Bangalore, like tier 1 user versus tier 2 user. So that is what we are in the process of building, that how can we understand user on the basis of their demographics as well, and how we can understand shared accounts. So that is what in the process of building for
So,
us.
so do you also perform price level segmentation
Huh. Pri-
when recommending to users?
Yes, exactly. That is one signal which we consume. Like price is a factor for us. That high ASP product should be shown with high ASP and not low ASP. That will be a very like low converting thing for us. So that is why we care about it.
You can take it offline. Yeah, go ahead. So thank you, Megha, for the interesting session. So next we have break till 11:10. Give a round of applause to Neha. And so install all your softwares required for the next session by Rajdeep Dua. It starts at 11:10. Catch you all at 11:10.
And this is like this only. It's on, right? Can you switch it? to do bit turtle. Yeah, it's not very clear. No, but how will people even? Yeah. Stopped. Okay. So it's bitly only. Yeah, that's fine. Yeah. Just creating a. Oh, no, yeah, there are a bunch of things they need to do. That will be customized. I can say fifth EL, right? I'll say SFDC, trans, right? TFAI, taken, trans, right? Yeah, yeah. It's on browser. Yes. Yes. Okay. So, yeah.
Hello, hello, check. Hello, hello.